Today we're going to study the alternating current and resistive load. Let's see if we have, for example, some power supply, okay, a varying power supply, and then we have some resistor. This is R. Now, this EMF, the voltage, the change in voltage given by the power supply is not constant, it's changing. Now we need to know how it's changing. It's changing in this form, so I can put E is equal to E max sine omega t. The reason I chose sine instead of cosine, because at time t equal to 0, I don't have any voltage. So I go something like this. This is time, this is E. So at time t equal to 0, I'm here. Now if you choose the cosine, at time t equal to 0, cosine 0 is 1, so you're going to have some voltage. So we chose a case where at time t equal to 0, we don't have any voltage. And then you start having the voltages changing like this. Okay? Now, if the voltage is changing, the current will also be changing. So, this current here, the reason we say is changing is because the electrons that's coming out of the power supply, they're going back and forth. Okay, so they go in groups and they have this drift velocity. So the drift velocity is really very small. The drift velocity, I put here V drift, is closer to 10 to minus 5 meter per second. So they're really moving very slow in the wire. Okay, so if you take an electron here, so the velocity, this is the drift velocity, is so tiny. But if you imagine you have some window, this is a window here. At certain time, this group here is going to pass. So you have certain amount of group of electron passing through some location, so through some point. So that's the current. How much charge you have passing per unit time through certain window. Now, the current, let's see, for example, if it's leaving here, like that, is going, and then is gonna turn back, these is gonna get pushed back and then go back like that. So you have this changing current, oscillating current going back and forth, and with certain frequency. And the frequency is there. Omega is 2 pi f. So the frequency of, what does it mean? Is the number of cycles per second. Number of cycles per second. For example, in a house, the frequency is 60 hertz. Okay? It means the current goes back and forth through the light bulb 60 times a second. Okay? Now, this current that goes back and forth is called an alternating current. Is changing, is oscillating. Now, let's look at the load. The load here is the resistor. This resistor, when it gets the current, it will go through it. So this resistor is not going to interfere with the timing. The current just comes in and goes back through the resistor like that. Okay? Now what happened? We can investigate Ohm's law. If I look at here the current, I put here the current through R. This is the current through R is equal to voltage I put here E. This is the voltage over the resistance. Now this E I put here E max because I have it here, sine omega t divided by R. Now this will give me E max over R sine omega t. Now this E max over R, this is Ohm's law. It's going to give us current I max. So this is actually I max sine omega t. So here is the current through the resistor. Let's look at the voltage through that's coming out of the power supply. Is this? It has that sine omega t. It's this one here. It's oscillating. Now the current also has sine omega t. So the current and the voltage are both oscillating with this sine omega t. So depending on the resistance, we don't know if the resistance is large or big. So the amplitude, if you look at here, we have these, if the resistance is big, you're going to have a big voltage. If the resistance is small, you're going to have big current. So we don't know, depending on the value of the resistor. So we can say that the current I put here, we can make it big, for example, like that. So the current is also oscillating. Is that the amplitude? It can be bigger or smaller. So I chose it to be big. So this is the current here. So you can see that the voltage and the current, they're both of them in phase. They're going in phase. You don't have a change of phase. One wave is not passing the other or behind the other. So if we look at phasors, for example, we assign, let's go to the trigonometrical circle. So here is the trigonometrical circle here, and here is the circle here. So we can say, for example, here is I, the voltage I is a phasor. So this phasor goes around like this, okay? So if we look at here, we have, let's look at the sine wave. We have 4 sections of the sine wave. 4. Let me use here color so you can see. I have this section, goes from here to there. I have this section 2, goes from here to there. I have this section 3, this quadrant here. And then I have section 4. 1, 2, 3, 4. So the phasor, when, for example, the voltage is going up, this phasor will go this location, will go this section here. This is quadrant 1. So when the voltage goes from here to there, let's call this point A. This is point B, C, D, and E. Now, going from A to B, here is A, you go to B. So, look at here, the voltage is increasing. So this phasor is going this way. It gets here to B. Then the voltage starts coming down. So the phasor is going to come down. Remember, it's rotating. It's here now. It's going to come down like that. That's the phasor. And this is quadrant 2. When it goes to 3, it keeps going down. Now the phasor is here in quadrant 3. That's the phasor. When you go from here to here, the last quadrant is 4. So the phasor is going up. When it gets here, it finished the wave. So these phasors, you see the current also has a phasor. The current also has a phasor, and they're rotating. Now for the current, okay, let me look at here. The current, like this one here, you see the current I. Remember what I had below is the voltage E. So the current phasor is also going in phase. The both of them rotating together like this in phase. There is some angle, let me call this omega t, which is theta. Theta is equal to omega t. So as time changes, these phasors are moving around like that together in phase. Okay? If, for example, was E ahead of I or I ahead of E, you would have the wave will look something like this. One will look like that, and the other one will look like this. But we don't have that case here. The resistor doesn't change the phase. The resistor doesn't interfere with the phase. It takes the energy from the system, radiates it, the energy comes out, but it won't interfere with the phase. It won't delay the current or delay the voltage. They go together. So this resistor here is called resistive load because it's a load. The circuit has to carry that load, which means it has to give it energy, it has to give it current, there is a voltage drop through it. So it's taking something from the system. So it's a load. They call it resistive load. Now, the alternating current is different from the direct current, DC. In DC current, this is DC current. The current is just going forward like that, one direction. Okay, like for the battery that you buy from the battery that you buy from the store, 1.5 volt battery. What happened? You hook it up to the wire. This is plus, that's minus. The current will go this way. I will go direct current. Let me make it going this way. One direction. Now for AC, it goes back and forth, back and forth. And then it has a frequency, okay?